Okay, on to chapter 5, and here in chapter 5 we're going to, not learn new laws like we did learning Newton's laws of motion, but rather apply some of the skills that we've learned to a very interesting special case, which is the case of something moving in a circle at a constant speed. And one of the reasons that this is an interesting motion, of course, a lot of things go in circle, but a great application of this is orbits of, like, the orbit of the moon around the Earth is pretty close to a circle. Orbit of the Earth around the sun is pretty close to a circle. And so we need to know a little bit more about gravitation. We've only discussed, the property of the gravitational force near the surface of the Earth, but we need to know how to describe it in general when you're far from the Earth or far from the sun. So we're going to practice with some of the things that we've learned in the previous chapters now. Start with a couple of voting questions. This one is looking at an object that's following some path, and at one point in time it's at this location down here. At a later time it's at this location, and the velocity vectors are what is shown. So in other words, it has the same speed because the velocity vector has the same length at the initial time and the final time. And the question here is, which of these, using our knowledge back from chapter 3, which of these answer choices best represents the direction of the average acceleration of this particle in between the initial and the final time? It's just a matter of the definition, but you may not remember. Think about it. Pause the video if you need more time. Okay, the answer can be gotten by thinking about the average acceleration is equal to delta v over delta t, where delta v is the change in the velocity vectors, and so the direction of the average acceleration is the same as the direction of the change in the velocity vector between initial and final, and the change in the velocity vector, v final minus v initial, can be gotten by placing the tails at the same location and going from the tip of the initial to the tip of the final. So it would be a vector that goes down and to the left like that. So it looks like D is the best choice, right? Average acceleration was defined as delta v over delta t, and we can think of the 1 over delta t as just scalar multiplying the delta v. So the direction of the average acceleration is the direction of delta v. This just changes the length of it. It's scalar multiplying it, but it doesn't change the direction. This voting question here is just based on your knowledge that you would have gained from the reading in this section. So here's an object moving in a circle at constant speed in the plane of the screen. At the instant shown, it's moving upward in the screen, and at this instant, which direction does the acceleration point? Up, down, left, right, or it's not accelerating at all. Sorry. And we'll move on to the answer. If you want more time to think, pause the video. The answer is, at that instant, it's accelerating to the left, even though it's moving upward, which may seem a little strange. Acceleration has a lot of non-intuitive kinds of properties to it, but that's one of the first things we're going to justify, is the fact that when something is moving in uniform circular motion, the direction of the acceleration is always going to point in the direction towards the center of the circle from wherever the object is at that instant. So I'm going to go through some derivations here. You certainly don't have to know how to reproduce these derivations, but it's interesting to see that the derivations actually are simple enough that you can understand them, even though the first time you see them they might seem like, a lot of logical steps. So I'm going to imagine something is moving in uniform circular motion on a circle of radius r, and at some time t1 it's at the location of the red dot, and it's moving with a speed v, so its velocity vector, of course, would be in the direction tangent to its circular path at that particular instant. So we're going to consider something moving on a circle of radius r with a constant velocity v, and uniform circular motion means, of course, motion in a circle, but the uniform part means that your speed isn't changing. So we'll just call that symbol v. And our goal is to answer these two questions. For an object in uniform motion, the direction of the acceleration is what, and the magnitude of the acceleration is what. Since we're talking about a vector, if I know everything about its direction and its magnitude, then that's all there is to know about the vector. So we're asking everything that we can ask about the acceleration for an object in uniform circular motion. Okay, so let's go back to the definition of acceleration, which was you have to consider over a very small time interval the change in velocity over the change in time. And as we looked at before, this is it's often useful to think of, if we're just concerned with the direction of this, we can think of, well, this 1 over delta t is just like a normal number. It's not a vector. So it is scalar multiplying the delta v, and that means it's not changing its direction, it's just changing its magnitude. 1 over delta t would be a positive number that's scalar multiplying it. So if I'm interested just in the direction of A, that means I'm interested in the direction of delta v when delta v is computed over a very small time interval. So in order to have a time interval, I've only got one point in time shown there. A little bit later, the objects might look like this. So it's over here at the dot located at time t2, still on the circle. The velocity vector is supposed to be the same length as it was at time 1. And we want to calculate delta v and figure out what its direction is there, at least when we make the times very close to each other. So in order to find delta v, one of the ways we discussed of doing it is to place the two vectors. You can always move vectors around anywhere you want in the plane as long as you don't change their magnitude or direction. Here we've lined up their tails, and then we said delta v, which is v2 minus v1, is just, it points from the initial vector tip to the final vector tip. So this is the direction of delta v, if these are my two vectors. Now those two vectors weren't particularly close in time, but we want to sort of consider what happens as this time gets closer and closer and closer to this one, because the acceleration is supposed to be what happens to that as the time interval gets really small. So let's look at a smaller time interval. These two times are really close together, or at least it looks that way from the picture. If I reconstruct that triangle I just drew there, it would look more like this. And as the times get closer and closer together, of course, v2 and v1, v2 is going to get closer and closer to v1, and as delta t goes to 0, these two vectors would be very close to parallel. And that means that delta v would be perpendicular to v1 as delta t gets closer and closer to 0. It's not quite perpendicular up here, right? That's not a right angle there. But this is very close to a right angle, and it's going to get even closer to a right angle. So the answer is the acceleration is going to be in the direction of delta v, and delta v is perpendicular to the direction of v. And the direction perpendicular to the direction of v at time t1 is at the location of this object toward the center of the circle. In other words, it's in this diagram it would be pointing sort of down and to the left at that instant. So let's fill that in. That's half of what we asked for. The direction of the acceleration for uniform circular motion is toward the circle's center. And it's just plain old acceleration for this particular kind of motion, but sometimes people give a special name to this kind of acceleration, centripetal acceleration. Centripetal means center-seeking, and that means it's just oriented from the location of the object we're watching toward the center of the circle. But it's still just plain old acceleration. This doesn't mean something new. It's just what the acceleration is doing when you're in uniform circular motion. Okay, so that takes care of the first question, and now we're going to address the second question, which is what is the magnitude of the acceleration when something's in uniform circular motion? And we expect it's not going to change as we go around because, although the direction of things is changing, certainly the direction toward the circle center is going to change. Every point on the circle kind of looks as good as any other, so we wouldn't expect the magnitude of the acceleration to depend on where we are in the circle. To find the magnitude of the acceleration, we can just use this expression and take the absolute value of it, or the length of it. If we want to find the length of A, that means the only place a vector appears in this expression was the delta v. So let's take the length of that delta v, and divide by t. So we're going to try to figure out what the length of delta v is. In order to do that, you just got to hang with me for a minute here. What we're going to do is label these two vectors that point from the center of the circle to the point at which the object is at time t1 and time t2 as r1 and r2. So r1 and r2 say, where is the object relative to the center of the circle? I just want a label for those. And I'm going to form a triangle over here that is, if r1 and r2 tell where it is at those times, delta r, which is r2 minus r1, is going to point from the first tip to the second tip. So there's another triangle. And in fact, these triangles are what are called similar triangles, and that's because when this radial vector rotates by an angle theta, the velocity vector is always perpendicular to it, so it's going to rotate by an angle theta. So if this angle is theta right here, I've just relabeled it in this triangle over here, this particular angle right here between the v's at those two times is also going to be theta. So we've got what are called isosceles triangles. That means two of their sides are equal in length. They're triangles made out of vectors, but they're isosceles triangles, and they have an equal angle that's in between the two sides of equal lengths. Now it's a little bit confusing to analyze this with the vectors on the triangle, so let's just take the lengths of the sides of the triangles. So the length of R1 and the length of R2, they're the same, and the name of those we just said was R before I changed this picture. So the length of those positions relative to the center of the circle is just R, the radius of the circle, and we'll call the change in the position of the object between time t1 and t2 magnitude of delta r. That's a scalar, just how big that vector is. Same thing here. Even though these velocity vectors are different, their lengths are the same, and we earlier on said we were going to call that v. So the lengths of these two sides is v, and this side would be the magnitude of the delta v vector. All right. Why are we doing all this? Because we're going to use a fact about isosceles triangles that have the same angle between these sides that are of equal length, and that is, if you have two triangles like that, they're what are called similar triangles. And similar triangles have the property that if you take the analogous sides on the ratio of two sides on two similar triangles of the analogous sides, their ratios are the same. In other words, if this side is twice as long as this side, then on this similar triangle, this side would be twice as long as this side. And that means the ratio of those two sides should be the same. 2 to 1 equals 2 to 1. Okay, so in terms of symbols here, that would mean that delta V over V is the same thing, same ratio as delta R over R. That's written down here. I color-coded them to see what triangle they correspond to. And all we're going to do is, since we have a delta V here, we're going to exchange out that delta V. Let's just solve for delta V and put the V up there. Okay, that means that delta V is V times delta R over R, and I'm going to substitute that into this expression over here. And what we get is, of course, we have a factor of V over R, and the delta V got replaced by a delta R, or magnitude of delta R there. Now we've got to consider that as delta t goes to 0, of course, V is the same everywhere on the circle, so it isn't affected by delta t, and R is the same at every location on the circle. Those don't change. So as delta t goes to 0, the thing that's going to change is magnitude of delta R over delta t. That just means how far you went divided by the amount of time that elapsed. And another name for that ratio is V. So we can rewrite this as delta t goes to 0, this part turns into a V, so I have V over R times V, or V squared over R. So in terms of the variables that we set out at the beginning, if you're moving in uniform circular motion, speed V on a circle of radius R, the magnitude of your acceleration is V squared over R. And those are the two important properties. Again, I know this is a bit more than most of the derivations we're going to do in Physics 110. You don't have to know this derivation. You have to know the ending parts of this, which is this property that's in the red box here. but it's sort of interesting to see and perfectly understandable at kind of a high school geometry level, as long as you understand how to think about those limits. Okay, so let's take a break with the video here, and we'll come back and start applying it.